why we're interested in these. So here were some of the best local functionals when we started our work. Scusaria, Purdue. They have no Hartree-Fock exchange. That's what I mean by local. They do pretty well for bonds, but not so well for barriers, not so well for covalent interactions. But they do better for transition metals because they have low X. So here's our best we can do with a local functional. It's actually pretty good. It's about as good as ML6 except barriers. It's really hard to get the barriers right if you don't put in some Hartree-Fock exchange. So this is a much faster calculation for complex calculations, gives excellent geometries. So one of the things we did was we made a new database for catalysis. I mentioned that we have a lot of data in a lot of databases. We did statistical analysis of these data. And we found smaller databases that were statistically representative of the larger databases. So for example, if you get those, whatever your mean error is on those bond energies tends to be your mean error on a much bigger set of transition metal bond energies. For main group bond energies, we look at the atomization energy, break all the bonds of these compounds up here. And we've showed that's statistically a good representation of much larger, more diverse databases. We've done the same thing for other things. Metal ligand bond energies are shown here. Various barrier heights for various kinds of reactions that you might have. And now with this smaller database, we were able to test a lot of the modern functionals. So we actually tested 35 different functionals, and these were selected from our previous tests of over 60 functionals as the ones that were most likely to do well. And we found that these 3 functionals developed in Minnesota were the very best of the 35, with mean errors on that database of 3 to 4 kcals. And the other functionals had errors up to 11 kcals. Here's some popular functionals. B3LIP has a mean error on this database of 5. Cambridge version of B3LIP, 5.5. Revised PBE, very popular in solid state, 6.5. BLIP, very popular, 7.3. PBE, very popular, 7.8. BP86, very popular, 8. So we were able to reduce the errors quite a bit here. I'd like to talk about gold clusters. So metallic nanoparticles can be very important in a variety of technological applications and also in geophysics. So there were some real questions about the structures of these gold clusters. So people made molecular beams of clusters with a negative charge on the clusters. So they're anionic gold clusters. So here we have some pictures of clusters with 11 gold, clusters with 12 gold, clusters with 13 gold. And you see you can have 2 kinds of structures. You could have a planar structure, or you could have a 3D structure, which is just another name for a non-planar structure. So Manfred Kappes did these beautiful experiments in Europe. He trapped the electrons and he did electron diffraction off of these size-selected clusters. And he found that the border between going from planar to 3D is quite high. It's between 11 and 12. Now for most clusters, you see here's aluminum. Of course, a 3-atom system would have to be planar. A 4-atom system could already be 3D. Neutral aluminum clusters are already 3D at 4. Silver clusters become 3D at 5. Here we see some clusters that become 3D at 7. Here we see some clusters that become 3D at 8. And well, what happens? Well, most of these methods predict that you actually stay planar in the gold clusters up to a much larger number. But we get the transition at the right place. Here was another paper. Here's a repeat of the gold 13. You can see these planar structure here. You can see a planar structure there, but you can see this 3D structure is lower. Here's the gold 8 with the cations, and you can see a variety of different structures. Here's 2 popular density functionals, PBE and TPSS from Purdue and Scusaria, and they predict that this structure here is the lowest, but we get the correct prediction that this structure here has the lowest energy, 0, and then the others are positive numbers with respect to that. So our functional is the only one that correctly predicts this 3D transition in both the cations and the anions. And so we think we've built in some of the features that are necessary to get the structures of the metal nanoparticles. Now the metal nanoparticles are very interesting because they don't have the properties of the bulk. So in a sense, they're a test for what you could get under extreme conditions when you get non-normal bulk properties for other systems. So we were very happy with that test. Here's one that I wanted to show. I thought it might be of interest to this group. Lattice constants of a perovskite material, lead titanium trioxide. In its low temperature phase, it's ferroelectric with a perovskite structure. And then it has a fairly high, unusually high Curie temperature where it goes to the paraelectric phase, which is cubic. So here we have experimental data on the lattice constants for the cubic and the tetragonal. The tetragonal is this one here, the low temperature one. And then here we have so this is a function I haven't talked about. It's a second order GGA developed at Minnesota that's particularly good for lattice constants, but doesn't have good properties for like barrier heights. Here's our MO6L, our general least expensive functional. And here's the mean error on those 3 lattice constants. And then here's Purdue developed especially a functional that was supposed to do lattice constants of solids. We actually do better than that. But this is a good general purpose functional, MO6L, and PBE-SOL isn't. Here's 2 other functionals from the Purdue group, especially PBE is very widely used for solid state work, and it has a much larger error. And we've actually looked at other solid structures, and this is not totally atypical. So here's acknowledgments. The work that I presented today, the development of the density functionals, was largely done with Yan Zhao, and the applications were largely done, the ones I showed today, with Nate Schultz, Mangira Mantina, and Rosendo Valero. Here's some people in my group right now that are currently working on various aspects of density functional theory. For example, Bo is putting our density functionals into the PWSCF program that Renata uses for a lot of geophysics applications. And he's in the back row, if anyone would like to talk to him. And so I think that's about the amount of time I was allotted.
Thank you, Don.
So sort of one notorious problem for local density and generalized gradient functionals, but particularly the local ones, is that they do badly with hydrogen bonds. And you didn't really
You mean
mention,
hydrogen bonds like non-covalent interactions, like in water dimer? That
yes,
kind of hydrogen bond?
I mean, and you didn't really mention any kind of testing of that, but
Well, I didn't accept that that one database had non-covalent interactions, and that includes a large number of hydrogen-bonded systems as well as dispersion-bound systems. So we've done a lot of testing on hydrogen-bonded systems. Oop, I went way too far. Must be getting closer. So here it says non-covalent. So you see we've greatly improved what you can do for the non-covalent interactions. There's a lot of hydrogen-bonded systems in there, pi-stacked systems, which have to do with adsorption on a pi system like an aromatic system. So that's actually one of the areas where actually pretty much nobody else has density functionals that work for these non-covalent interactions. But we do. So people sometimes call these dispersion-like interactions, but in addition, of course, the hydrogen bond has a large electrostatic and partial covalent character. So we're able to treat a broad range of, we can treat charge transfer, which a lot of density functionals have a problem with too, but we can treat charge transfer complexes. So that's actually one of our successes. I didn't emphasize it because I didn't know how. Well, I only had 20 minutes.
Mm-hmm. The local version, is that successful for hydrogen bonds as well?
Not really. Not really. It doesn't really have some density functionals. There was a period where people said some of the density functionals seem to be doing better on the non-covalent interactions than they ought to. But people discovered that these functionals, like the local ones that don't have good performance across the board, they were often getting sort of reasonable binding for the wrong reason. It was coming out of the exchange functional, but it's supposed to come out of the correlation functional. So they had large errors in exchange, and it sometimes was giving spurious binding. So they couldn't really get the trends right. They couldn't get good quantitative. So now it's generally believed that the local functionals do not do a good job. But our MO6L does. But it's not this kind of local that most people do because it has the kinetic energy density.
But in this case, in the hydrogen bond, it definitely depends on the pressure. On how much you squeeze the hydrogen bond.
So
suddenly, the local functions start working when the hydrogen bond is short.
Well, that's possible. Sure, okay, if you say so, I believe you. I mean, all right. But I wouldn't trust the local functionals. They're not good across-the-board functionals. And so when they work, you kind of worry that they're working for the wrong reason. I sometimes think that people use the local functionals just because they're in a lot of programs and they're not expensive, but they're not the best functionals.
Do I understand correctly that you have some empirical parameters which are obtained by fitting to the experiments, or?
That's correct, we do.
How many parameters do you actually have in
the
latest functionals?
In the latest functionals have 30 to 50 parameters. So this is a question that comes up a lot. Some people don't like parameters. We had some functionals that had only one parameter that did pretty well, and then we went to functionals that had 6 parameters and they did better. And we felt we were learning how to design the correct functional forms. And so we got large, diverse databases, and we started going to higher order polynomials in our functionals. And we found we could go to 20, 30, and 50 parameters, and we got stable results. We could predict results that were outside of our training set. So for the most part, we're willing to accept this larger number of parameters because we think we're getting it's just a convenient way to represent a complex function.
Do these functionals work well for metals?
Yes, they do work well for metals. So that's what that TM column is. It's transition metal bond energies and reaction energies. In fact, MO6L has better performance for metals than any functional I know of.
And mod insulators?
Mod insulators are pretty hard, and we've looked at some model problems that are related to mod insulators, but we haven't directly looked at mod insulators. We'd like to do that.
Okay, JJ. Oh, sorry.
Go ahead. Real quick, which codes currently incorporate your functionals?
Okay, on my website, there's a list of quite a few codes that have our functionals, and you can go there. But Gaussian has our functionals. QChem has our functionals. Jaguar has our functionals. NWChem has our functionals. Games has our functionals. Amsterdam Density Functional has our functionals. So there's quite a few. There's even more. Those are the ones we tend to use that have our functionals.
JJ.
For the standard GGA versus LDA, people say that the GGA overestimate the static volume and LDA underestimate a little bit. How about you? This new for the solid, for the mineral solid?
Well, we've done a limited amount of work on solids, but we seem to get very good lattice constants with MO6L and with SOGA, which is not a general purpose functional. But we seem to get very good lattice constants. We seem to get excellent geometries for both solids and molecules with MO6L. And with MO6, they're almost as good.
As good
as MO6L, which in one paper we wrote, MO6L had the best performance for solid state lattice constants.
With or without 0.1?
Yeah, that's my next question. With or without the...
Well, when we do tests, so there's two ways to do tests of geometries. One is to calculate the potential surface and then put in the vibration and say, oh, the 0-point vibration, because it's anharmonic, shifts the lattice constants or the bond energies if it's a molecule. We tend to do it the other way. We tend to try to make the best possible estimate of how big that shift is and correct the experimental data to get the actual equilibrium structure, the place where the potential energy has a minimum, and then we do that comparison. But what we don't do is run the calculation without vibrational effects and compare to an experimental value that's influenced by those effects. We try to do it consistently one way or another. So when I talk about comparisons, they're consistent comparisons. But if you would do this anharmonic shift accurately, you'd get a very similar conclusion, either way of doing the calculation. So we feel that the proper thing to do is to have a calculation that doesn't have the vibrational effects in, agree with the potential surface that doesn't have the vibrational effects in. Some people say, well, I can't really afford to do it right, so I'd like to build in errors. I'd like to build in so that my functional, without putting in the quantized 0-point vibrational motion, predicts the experimentally observed structure. But we think that that game will get you only so far. It's building in cancellation of errors, so we don't like to do that.
Maybe I missed it, but did you discuss band gaps at all?
I didn't discuss band gaps. Band gaps are very difficult. The MO6L does better for semiconductor band gaps than any other local functional. But band gaps are very difficult. We're working on it in our group right now. But we've had some success, but they're very difficult. I would say it's a problem for all density functionals right now. Although Scuderia has a functional called HSE, Hyde-Scuderia-Ernzerhof, that seems to do very good on band gaps in general. But that functional is what's called a range-separated functional. So you take the Coulomb interaction and you take an error function and a complementary error function and you break it into two parts. And you use exact Hartree-Fock exchange on one part of the Coulomb interaction and you use density functional exchange on another. It's a very nice strategy. It's a strategy we're looking into using in our group right now. However, it does limit you on the number of computer codes that you can do because most computer codes don't have that capability to handle that range separation yet. But Scuderia has probably been the most successful on the band gaps.
It looks absolutely thrilling. Where do you see limitations of these functions? For instance, you have fitted these parameters on a certain number of properties. Some properties, even on the